Welcome to our lecture on methods of variation parameters and inverse differential operators. We'll first discuss the method of variation in parameters, and then we'll go on to discuss differential operators and how inverse differential operators are used to find a particular solution to a non-homogeneous equation. So we discussed last time only variation parameters for ODEs that were of order 2. Variation parameters also works for ODEs that have order larger than 2. Notice you always get, for a linear ODE, you always get a linear independence of these in solutions. By the way, this should be a naught times y. And to find a general particular solution, u1 y1 plus un yn, you need to solve this system. u1 prime y1 plus u2 prime y2 plus un prime yn is 0. u1 prime y1 prime plus u2 prime y2 prime plus un prime yn prime is equal to 0, all the way down to u1 prime y1 to the n minus 1 plus u2 prime y2 to the n minus 1, all the way to un prime times yn to the n minus 1. This means the n minus first derivative is equal to q of x, the term on the right-hand side, divided by an, the coefficient of the nth derivative of y. So it's very similar. These are inequations in n unknown functions, u1 prime through un prime. You can solve these inequations for those n functions and then integrate to get the original functions. So this is an example how it plays out. Find a general solution to y triple prime plus 3y double prime minus y prime minus 3 is equal to 2e to the x. First, we get this characteristic polynomial r cubed plus 3r squared, factor out r squared plus r plus 3 minus r plus 3. We're left with r squared minus 1 times r plus 3. What are its roots? Negative 1, 1, and negative 3. The complementary function is c1 e to the negative x plus c2 e to the x plus 3c3 e to the minus 3x. Particular solution will have the form u1 of x e to the minus x plus u2 of x e to the x plus u3 of x e to the minus 3x. We therefore need to solve the following system. u1 prime e to the minus x plus u2 prime e to the x plus u3 prime e to the minus x, negative u1 prime e to the minus x plus u2 prime e to the x minus u3 prime e to the minus 3x, 0, and then this last equation, u1 prime e to the minus 3x plus u2 prime e to the x plus 9, u3 prime e to the minus 3x. So each time we just differentiated these functions, the linearly independent solutions to the associated homogeneous equation. If you add the first and second equation above, you get the following. That eliminates u1 prime. You add the second and third equation, you also eliminate u1 prime, and now we can subtract these two equations to get a u3 prime. We eliminated u2 prime. A u3 prime e to the minus 3x is e to the 2x. Solve for u3 prime, 1/8 e to the 5x. That's just multiplying e to the 3x on both sides. So we get u3 prime is 1/8 times e to the 5x. u3 is 1/40 e to the 5x. And we're going to plug in u3 prime is 1/8 e to the 5x into the first two equations. u1 prime e to the x minus x plus u2 prime e to the x plus 1/8 e to the 2x is 0, minus u1 prime e to the minus x plus u2 prime e to the x minus 3/8 e to the 2x. We add these two equations. What do we get? 2u2 prime e to the x minus 2/8 e to the 5x. Solve for u2 prime, 1/8 e to the 4x. That's just from multiplying both sides by e to the minus x, e to the 5x, times e to the minus x is, of course, e to the 4x. Divide both sides by 2. We get u2 prime is 1/8 e to the 4x. That means u2 is 1/32 e to the 4x. Now we have u2 prime and u3 prime. We plug those both into the original equation and get the following. u1 prime e to the minus x plus 1/8 e to the 4x times e to the x plus 1/8 e to the 5x times e to the minus 3x is 0. That means u1 prime is e to the minus x plus 1/8 e to the 5x plus 1/8 e to the 2x is 0. We solve that for u1 prime. Just bring e to the 5x, e to the 2x to the right-hand side. They both have a coefficient of 1/8. Multiply both sides by e to the x. E to the 5x becomes e to the 6x. E to the 2x becomes e to the 3x. Integrate, we get negative 1/40th e to the 6x minus 1/24th e to the 3x. And now we're going to plug these three functions, u1, u2, and u3, back into the original formula for yp, the particular solution. We get the following. So these first two terms, negative 1 over 48 e to the 5x and negative 1 over 24 e to the 2x, came from these two terms. And the last two terms came from 1/32 e to the 4x times e to the 2x and 1 over 40th e to the 5x times e to the 3x. Negative 1/60th e to the 2x plus 1 over 32 e to the 4x plus 1 over 16 e to the 5x. This negative 1/60th, if you notice, comes from these two terms, negative 1 over 24 times e to the 2x plus 1 over 40 e to the 2x, so it becomes negative 1/60 e to the 2x. And then we have these two terms left over, 1 over 32 e to the 1 over 32 e to the 4x. And we plug this back into the original equation. Differential operator is an operator that includes derivatives and acts on functions. D is d dx is an operator that takes the function to its derivative. D of sine of 2x is 2 cosine of 2x. That just means differentiate that function. We can rewrite y double prime plus y as d squared. That means act on a function by differentiating and then differentiate again. Add 1, we get cosine x. Operator is linear if it consists of sums of terms that are all multiples of d to the n, where n is a non-negative integer. That's pretty straightforward, because if you differentiate a function n times, undoing it is integrating a function n times. Now, you have some limit sign problems based on this. Find a linear differential that annihilates, that means sends to 0, e to the 2x plus 1 squared. Boil the expression in the parentheses to get the following, e to the 4x plus 2 to the 2x plus 1. That means d minus 4 annihilates e to the 4x, d minus 2 annihilates e to the 2x, you can check this, and d annihilates 1. So if you let all these act on e to the 2x plus 1 squared, it will annihilate that function. You can check this because d annihilates the constant terms. D minus 2 annihilates all the terms involving e to the 2x. What are we left with? Just terms that involve e to the 4x. And d minus 4 annihilates e to the 4x terms. So they're linear, so any multiple and sums of those terms will also be annihilated. So therefore, if you compose this operator, differentiating, do the derivative of minus 2, then do the derivative of minus 4, it will annihilate this function and we'll get 0. Now, a polynomial differential operator, or a linear differential operator, an times d to the n, an minus 1, d to the n minus 1, an minus 2, d to the n minus 2, all the way to a1, d plus a naught. That just means you take a polynomial evaluated at the differential operator d that takes a function to its derivative. Its inverse is an operator such that when you act on q of x, will give the particular solution. P of d is equal to yp. Notice this is a non-homogeneous differential equation of order n, and a term on the right-hand side is q of x. Now, the inverse of d to the n, as we said before, is to integrate n times. Now, if a is a constant and q of x is b to x to the k, the inverse of the operator d minus a is the operator d minus a to the negative 1, which is negative 1 over a, 1 plus d over a plus d over squared over a squared, all the way to dk over ak. That means we're acting we are adding these k plus 1 terms in the parentheses here, and notice that dependent upon the power of x in the term q of x. Another important thing is that if the polynomial splits in factors into the product of two polynomials, the inverse is the inverse of the operator that acts on first times the inverse of the operator that acts on second, or d inverse times q of d inverse. So here's an example of how that plays out. Let's find a particular solution from y double prime plus 2y prime is x. You rewrite this equation as d plus 2 times d is y is equal to x. That means differentiate a function, get y prime, then differentiate that what you got and add to 2 to what you got. So P of d is d plus 2 times d. Its inverse is d inverse times d plus 2 inverse. So again, what appears on the right comes first, d inverse, d plus 2 inverse. D inverse, d plus 2 inverse of x. Notice d plus 2 can be written d minus negative 2. So a is negative 2. We get 1/2, 1 minus d over 2x. So we get, what happens when you differentiate x? We just get 1. So 1/2 parentheses 1 minus d over 2 acting on x gives you x minus 1 over 2. Multiply by 1/2, you get x over 2 minus 1/4. Differentiate again, or rather now apply the inverse operator of d, that just means integrate, and ignore the constant of integration. You get x squared over 4. That's the antiderivative of x over 2, x squared over 4 minus x over 4. And then you can check, indeed, if you differentiate this, you get x over 2 minus 1/4. So we get x over 2 times 2, that's x, minus 1/4 times 2, which is negative 1/2. You differentiate this twice. And if we differentiate this function twice, what do we get? We get just 1/2, right? This goes to 0. It's negative 1/4. The derivative of negative 1/4 is 0 because negative 1/4 is a constant. The derivative of x squared over 4 is x over 2. The derivative of x over 2 is 1/2. 1/2 minus 1/2 is 0. We're left with x. Okay, so that's it. We'll be talking later on about the simple harmonic oscillators and how linear differential equations, whether homogeneous or non-homogeneous, are applied to physical situations you see in real life.